Hey guys, I'm trying something new today, and as you know, when you try something new, it could go very right or very wrong. We're just gonna have to see. I'm sitting here with an old microwave that we have here, and as we've been learning in class, microwaves are a form of light, electromagnetic radiation. We can't see it, our eyes can't make use of it, but it can be used to heat up food. I recently read an article that said there's a quick and easy way to verify the wavelength and frequency of the microwaves that your microwave uses simply using a chocolate bar. So we're gonna see. What I read was that if you take out the rotating plate and put the chocolate bar inside without giving it a chance to rotate, we should be able to see something. I'm gonna start with 20 seconds and see if that's enough time to see what we wanna see. All right, so after 20 seconds, we're gonna take a look, and I'm not seeing any wavelengths quite yet, so I'm gonna try another 20 seconds. All right, after another 20 seconds, what do we have? Ooh, okay, check this out. So what I'm seeing here is I definitely have a couple of different zones where some melting has occurred, but then in the middle, there's places where there's no melting. So I'm touching this, that's very solid still. But right over here, that's super melty. Oh, wow, that's really melty. Yikes. I'll show you a close-up of my chocolate bar again. Again, right over here, that's pretty solid. And right in here, that's also still solid. But somehow the waves, the microwaves, have interacted right along here and over in this corner to melt those areas while not melting this area. So this kind of tells me that maybe this is one of the peaks or troughs of the wave, and the other part of the wave is not interacting over here. It seems like there's a definite distance between here, and I'm wondering if that would correspond to the appropriate wavelength. I'm just estimating, of course, but if I were to pick another parallel line over here and assume that the wave is traveling here and then hitting here again, I'm wondering what the distance between those two parallel lines would be. I'm guessing from this about 10 centimeters or so. We've been learning that the wavelength and the frequency of light is related by this equation. If you take the wavelength times the frequency for any photon of light, you multiply them together and you will get a constant, the speed of light, which we're estimating here at 3 times 10 to the 8th meters per second. In general, as the wavelength of light would get smaller, the frequency would have to get larger so that they multiplied together to equal the constant. And the opposite would occur too. As the wavelength gets larger, the frequency would get smaller. Now the wavelength that I'm measuring off of my chocolate bar, I'm estimating 10 centimeters, which is 1/10 of a meter. I have to put it in meters. So if I do my math, 3 times 10 to the 8th divided by 0.1, I will get 3.0 times 10 to the 9th. And that, when the meters cancel out, will give me seconds to the -1, or a unit of hertz. So 3 times 10 to the 9th hertz is 3 billion hertz, or 3 gigahertz. You could also say 3,000 megahertz. That is my estimate of the frequency of my microwave. Let's go see how we did, shall we? In the article I read, it said that most microwaves actually have written somewhere on one of the labels what the frequency of this microwave is. I never noticed it before, but I did find it over here along this edge. I'll show you. All right, so there's this label on the inside of the microwave, and right down there, it's going up and down, but it actually says the microwave frequency is 2450 megahertz. Now my calculation of 3000 megahertz is a little bit off, but I would expect that because I'm kind of using a chocolate bar and a ruler and I'm kind of making estimates. But for an estimate, I think 3000 megahertz is pretty good. And I think that it pretty well proves what I was reading, that you can check the frequency of your microwave by using a chocolate bar. Who knew?